Pappas from the Chemistry and Biochemistry Department at Ohio State, and I'm with Dr. Michael Lisa, Professor of Physics at The Ohio State University, and today we're going to talk about nuclear power. There's ongoing discussion about nuclear power, but I think that students in Ohio would be amazed at how high the percentage of their electricity comes from nuclear power. I got the little breaking up of from AEP, and we are now for 2015 projected to get 34% of our electricity from nuclear power. If you could start off by describing the process of nuclear fission, please.
Sure. Well, nuclear fission is a nuclear reaction which releases energy. This energy is captured as heat, boils water and turns a turbine, just like a coal power plant heats up water, turns a turbine. The way it works, just like a chemical reaction, you have components of the nucleus and they get rearranged. So in a chemical reaction, you rearrange the electrons, they have different energy levels. The same thing is true in a nucleus. Fission comes from a competition between two forces. You have charged protons inside a nucleus. Since they're having the same electric charge, they'd love to fly apart from each other. But there's another force in the nucleus, not really relevant for electrons in chemistry, and that's the strong force. It's called strong because it can overcome the strong repulsion, the electric repulsion between the protons. It only works at small ranges. So if I have a nucleus and I can separate just slightly two clumps of nucleons, protons and neutrons, now the strong force is no longer active, and the Coulomb repulsion generates a huge repulsion between the charged clumps of nucleons, which is to say, two nuclei, and that's nuclear fission. Some nuclei, especially the large ones like uranium, are just on the hairy edge of nuclear fission. There's a competition between the strong attractive force and the electrostatic repulsive force, and it just takes a little vibration to generate two pieces that become sufficiently separated that they fission. And tremendous energy is released, and it's really electrostatic energy.
That's fascinating, yes. Could you describe how this relates to Einstein's equation E equals mc squared?
Sure. So a lot of times, once again, I'll make a connection with chemistry. A lot of times in chemistry, one will talk about the conservation of mass, and it sounds like a nuclear reaction will violate the conservation of mass law. It's not an apparent violation, it's a real violation because there is no such thing as the conservation of mass law, either in nuclear physics or chemistry or at all. That was Einstein's point. If I would think about chemistry, the strongest chemical bond, I think anyway, is for carbon monoxide. And if I take the mass of a carbon atom and a mass of an oxygen atom and add them up, I'll get some number. If I now combine them and make carbon monoxide, and I take a look at the mass of carbon monoxide, it is less than the mass of the carbon and the mass of the oxygen by a small amount, 1 part per billion. So this part per billion of the mass of carbon monoxide, if I multiply that by c squared, a large number, that is the energy I get out of that reaction. That was Einstein's point, is that if I get energy out of a reaction, the result weighs less, it has less mass. That's a small effect with chemical bonds. Carbon monoxide is the strongest one, it's about a part per billion. Nuclei, it's the same sort of thing. I have components, I'm not talking about electrons, I'm talking about protons and neutrons. And if I rearrange them, bring protons closer together, a little further apart, something like this, I can get energy changes of parts per million. I should say parts per thousand, doesn't matter. In other words, the reactions are 1,000,000 times stronger. So with chemistry, it's part per billion. 1,000,000 times stronger means with nuclei, it's part per thousand. Okay, so 0.1%. That is much more noticeable. So a nuclear physicist would never think that there's conservation of mass. And a chemist shouldn't think it either, but they can get away with it because it's 1,000,000 times smaller.
Significant figures.
So if I undergo fission, that's exothermic, that means the parent nucleus weighed more than the sum of the nuclei that came out. And that difference in mass, times c squared, is the energy we get out.
The speed of light, 10 to the 8th.
Yeah.
10 to the 16th, phew, there we go. And that is the great advantage of nuclear power.
Well, it is. I mean, if I have each reaction is 1,000,000 times more releases 1 million times more energy than a chemical reaction, then I need 1 million times less, fewer reactions to generate the same power. That's why nuclear waste, the output of a nuclear reactor, is 1 million times less mass than for a typical fossil fuel plant.
Yeah.
And of course, when I talk about nuclear reagents, it's often denser than, for example, fly ash or carbon dioxide, which gets emitted. So in terms of volume, it's not even a comparison. That is one advantage of nuclear.
Yes, and when you compare it to something like coal, you were saying before the amount of coal that has to be burned to get anywhere near the energy that is needed is tremendous. And
yes, it's tens or even 100 cars of coal per day at a large coal plant. And you know, I told you the conservation of mass is not a real principle, but it's good enough to a part per billion in chemistry. That means those 100 cars of coal is now coal waste. That means fly ash, that means sludge ponds. And you know, we talk about where should we store nuclear waste, and that's a real issue. But where do we store coal waste? Well, we store it in our lungs, we store it in our water, store it in the air, and we know what that does. Sludge ponds. You know, if you've ever been to one of these fly ash pits or a sludge pond, you say, you know, I would much rather live next to a nuclear reactor. I mean that in all honesty.
Mm-hmm. Well, there's less radioactive material coming out of a nuclear power plant than there is a coal-burning power plant.
That's right. So there's less of everything coming out of a nuclear power plant. I mean, if you drive by a plant and you see big plumes above it, I remember one of my kids saying, look at all the smoke coming out of that plant, a plant in New Jersey where I'm from. I said, you know, that's water. That's all it is. I mean, it's boiling water, and then that's the steam. And coal plants and nuclear plants and natural gas plants all work the same way. Boil water, turn a turbine, and then so most of it is water. In a coal plant, there's also a chimney with smoke. Nuclear plant, no. All waste is contained. Nothing goes into the air. With coal, it naturally must go.
Mm-hmm. And one of the disadvantages, though, is the storage. I know that Yucca in Nevada, the Yucca Mountains, is, what do they say? What happens in Vegas stays in Vegas. This is like a half an hour drive from Las Vegas. And they have planned to put it there for many, many years. And is that now an operating, are they storing now, or they
No.
Okay.
No. There's
Has it been halted?
Yes, it's sort of been mothballed, and that awaits future action. I mean, it's what we need to do. I mean, Yucca Mountain is geologically stable. It's not far from where people live, but it's certainly far enough that it won't affect anything. I mean, after all, you need trucks and so forth to go there. It's a safe place. Right now, all spent nuclear fuel, you can call it nuclear waste, but actually, if you're France, you reprocess and get more energy now. But so spent nuclear fuel is stored on site at our facilities, either in cooling ponds or in dry casks on concrete slabs. And you know, the workers park their car, walk by them every day. There's no danger to it. I mean, there's no danger at all. You know, unless there's an accident. And that's what people say. Is, you know, it's fine until there's an accident. It's worthwhile keeping in mind that the number of deaths from any nuclear operation in the U.S. Has been, over all of history, about a dozen. Okay, then that comes from problems. I mean, that's a failure of safety. Meanwhile, the safe operation of a coal plant, operating as specified, as on a day-by-day normal basis, will kill more people today in the United States by 5 o'clock than were ever killed in the U.S. by nuclear power, ever in all of history. And that is a cost of doing business with coal. Yeah. We would never tolerate that with almost anything else.
Yes, and that doesn't also include the people who have the black lung disease.
Right, the miners, that is right. So this is largely from being released into the environment. And, you know, it's, in some sense, it's a slow process, and you have to look at this. It's like saying cigarettes kill people. Because you could say, well, look, these people who died from breathing in too much soot and so forth, it's a statistical thing. They would have died of something anyway. That's true anyway. But just like cigarettes kill, so does soot from coal. It's particulate, it's cancer-causing, and it's radioactive.
Yes. Oh, yes. Definitely. Well, thank you so much for spending some time with us today.